In this video, we are going to walk through an example of how to find the acceleration in a system that involves two masses connected by a string and a pulley on an inclined plane. So let's jump right into this example. This says, in the diagram below, a 10 kilogram mass is placed on a frictionless 30-degree incline relative to the horizontal and attached to a 15 kilogram mass with a string. Find the acceleration of the system. So I've gone ahead and sketched out this situation. We have this inclined plane at an angle of 30 degrees relative to the horizontal. We have this first mass, which is 10 kilograms, connected to a string and a pulley to another mass hanging over the edge that is 15 kilograms. Now, our question is, what is the acceleration in this system? So in this type of scenario, because this mass is larger than this mass, I'm going to make the assumption that the acceleration is going to be in this direction. So the larger mass is going to pull the smaller mass up the incline and over the edge ultimately. So to actually find what the acceleration is going to be, we need to identify what are the forces that are acting on both this first block and this second block. So if we consider just this first block here, we know that gravity will be acting on this block, and the force of gravity will be straight down, like this. Now, the force of gravity is simply equal to the mass of the object times the magnitude of gravity. So let's call this mass, let's label that M1 for mass 1, and we'll say this one is M2. So the force of gravity on this mass is just going to be M1 times the magnitude of gravity, g. Now, we can break down this force into its components. So we'll have a perpendicular component that's perpendicular to the inclined plane, and we'll have a parallel component that is parallel to the inclined plane. So instead of working with this force directly, we're going to work with its two components. Now, one thing we have to realize is that this angle right here is exactly equal to this angle. So this will also be 30 degrees. Now, if that's not obvious why that's the case, just consider this fact. Right here, we have a right triangle where this is a 90-degree angle because remember, the force of gravity is perpendicular to the horizontal. And what we know about a triangle is that the three angles of the triangle must add up to 180 degrees. So if this is 90 and this is 30, that's 120. This missing angle right here must be 60 degrees. So let's write that, 60 degrees. And one other thing that we know is that this angle right here is also a 90-degree angle because remember, we drew this line parallel to the inclined plane. So if this angle is 90 and we know this is 60, then this little angle must be 30. So that 60 plus 30 add up to 90. So that's why these two angles are equal to each other. Okay, so once we've established that fact, now we need to know what's the magnitude of these two components right here. Well, this perpendicular component is simply going to be the force of gravity times the cosine of this angle. So let's write that down. M1 times g times the cosine of 30 degrees. And this parallel component, that's going to be M1 times g times the sine of 30 degrees. Now we also have to recognize that there will be a normal force that is opposing this perpendicular force, and it will be an equal and opposite force according to Newton's third law. So this, let's write N, this normal force is also going to be equal to M1 g times the cosine of theta, which is 30 degrees. So what we'll notice is that these two forces are actually going to cancel each other out, and the only force that we'll be concerned with acting on this block is this force right here. Now for this second block right here, it will also have gravity acting on it. So the force of gravity is going to be M2 times g. So let's draw a little arrow. M2 times g. So ultimately, the only two forces that we have to worry about are this force right here and this force right here. So what we can say, according to Newton's second law of motion, is that the net force acting on this system is simply going to be equal to this force, which remember we said, let's assume the acceleration is in this direction. So we'll call this a positive value, so M2g. And we'll say that this force is headed in the negative direction, so it's opposing this direction. So we'll say minus M1g times the sine of 30 degrees. And what we know about Newton's second law of motion is that the net force must be equal to the mass times the acceleration. So in this case, we have two masses, 10 and 15. So what we can replace this net force with is M1 plus M2 times the acceleration must be equal to this whole quantity right here. So let's write that, M2g minus M1g times the sine of 30 degrees. So now that we've written out this equation, we have everything that we need to solve for A, the acceleration in the system. So let's go ahead and fill in all the values that we know. So m1 plus m2, that's 10 plus 15, which is 25. So we'll say 25a is equal to m2, that's 15, times g, the magnitude of gravity, that's 9.8, minus m1, the mass of the first block is 10, times the magnitude of gravity, so 9.8, times the sine of 30 degrees, which turns out to be 1/2, or 0.5. So if we simplify a little bit, we get 25a is equal to 15 times 9.8, that turns out to be 147, minus this quantity, that turns out to be 49. So we end up with 25a is equal to 147 minus 49, that's 98. To solve for a, we'll divide both sides by 25. These will cancel out and we'll be left with a is equal to 98 divided by 25. That comes out to about 3.92. And we're talking about acceleration, so our units will be meters per second squared. So that will be the acceleration in this system. So that is how you can solve that type of problem. We just have to realize that ultimately there's only two forces that will be working on this system. So to find the acceleration of the system, we just have to identify one of these forces as being a positive value and the other one as being a negative value. And once we've done that, it becomes very straightforward to solve for the acceleration.